Hey everyone, let's practice together a systems design problem on designing an AI chatbot system. Okay, so we're going to learn together how to do this. So we're going to choose Tutor Taylor to get started. Hello.
Hey, I'm Taylor. I'll be tutoring you through designing an AI chatbot system, and we'll work through it together step by step. To kick off, what are the core user actions and success metrics you want to optimize for in this chatbot?
Yeah, I would want to optimize for the number of users and also latency. So I want like quicker replies.
Cool. So we care about scale in terms of number of users, and we care about low latency replies. Let me sketch the simplest starting point, then we can refine it. When you say number of users, what peak concurrent users should we design for?
I'm dreaming big. Let's say like 1 million concurrent users. We're the biggest company in the world and we own a bunch of market share of the chatbot system.
1 million concurrent is a good target. Let me update the sketch to reflect that scale focus. Now, what are the core user actions you want the chatbot to support in the first version?
Okay, so can you give me a minute to think about this? Yeah, so I'm thinking out loud. Core user actions. Well, we want the user to be able to chat, right, with the chatbot. There's a lot of interesting things we could do that modern AI chatbot systems can do today, like chat and have RAG with other chats, right? Or search. We can pull in searches and stuff. But for our first version, let's just focus on being able to log on and view past chats that we've had and create new chats and be able to chat with the chatbot back and forth.
Great. So V1 is log in, create a new chat, send messages back and forth, and view past chats. Let me update the diagram with those user actions and the main backend pieces we will likely need. Now that we have the actions, what latency target do you want for a typical message response, like under 300 milliseconds or a few seconds?
Yeah, let's try to make it under 1 second. This seems good enough.
Under 1 second makes sense. Let's deep dive on multi-turn context. When a message comes in, where do you store the conversation state so any chat service instance can pick it up, and what do you keep in that state? Let me redraw the current architecture so we can annotate the state path. Here, the key question is whether the chat service reads and writes context from the chat store on every turn, or whether you introduce a separate fast state store for the active conversation window.
Oh, that makes sense. Wait, so how does a fast store work? What is a fast store? Yeah, what is it?
A fast state store is just a low latency place to keep the active conversation context so any chat service instance can fetch it quickly instead of reading the full chat history from the chat store every turn. Let me update the diagram to show that split. The chat store is your durable source of truth for all messages, while the state store holds a small rolling window like the last n turns, plus metadata like a summary, tool results, and an expiration time. Let me draw that state path. In this picture, on each message, the chat service reads the active context from the state store, calls the model service, then writes the new message durably to the chat store and updates the state store for the next turn. What would you put in that state store value for one conversation? And how big would you cap it?
Oh, so based on what you're saying, sounds like we could store basically the conversation, right? So it'd just be the conversation histories back and forth. And there is a context limit to the models, so we could store up to the context limit of a model, and then past that, there's no point.
Yes, exactly. The key is you usually do not want to store the entire history there. You want a bounded context window plus a summary so it stays small and fast. How would you handle the moment when the conversation grows past the model context limit? Do you summarize older turns, drop them, or keep a hybrid of summary plus last end turns?
Oh, that's a good point. Yeah, let's keep a hybrid of summary and the last entrance, just so we have the context of the full conversation.
That hybrid approach is the common pattern. Keep a short window of the most recent turns plus a running summary of everything older. When you update that summary, would you do it synchronously on the user request path or asynchronously after you've already returned the model response?
What would the pros and cons of each of those be?
Synchronous summarization keeps the summary always up to date, so the next turn is consistent, but it adds latency and can fail the whole request if the summarizer is slow or down. Asynchronous summarization keeps the user path fast and isolates failures, but you can have a brief period where the summary is stale, so you need a fallback like using last end turns only or doing an on-demand summary if the state is too large. Which way would you choose given your under 1 second latency target?
Yeah, I mean, now that you mentioned the 1 second latency target, let's use the async because we're gonna have a lot of messages, a lot of chats going on at the same time, and sometimes we can't always get to them. But being able to like failing in this right isn't the worst case. If the user is unable to see the context, they might not even notice, and in the worst case, this only affects X% of our users. So let's go with async.
Async makes sense for your under 1 second goal, and you can treat the summary as eventually consistent state. What if the user sends the next message before the async summarization finishes, and the state store is still over the size cap? What fallback would you implement on the request path in that case?
Oh, so if the summarization isn't done yet, then we can go ahead and return the last end messages that fit under the cap.
Good. So you would just use the most recent turns that fit under the cap and ignore the stale summary for that request. What if even the last n turns still do not fit? For example, because a few turns are huge. Would you truncate, do a quick on-demand summary on the request path, or reject the message as too large?
Oh, that's a good point. I would. I'd reject it. Well, no. Okay, we should still fulfill our user requests. Um, we could do summary. I suspect that most of our users wouldn't have two messages that are like 1,000 tokens, right? Or sorry, 100,000 tokens or something. And if they do that, then that's not a very common use case. So yeah, actually, let's reject the message.
Rejecting is reasonable as a safety valve, but I would make it a clear product rule like a max input size, because it is otherwise an easy way to blow up latency and cost. If you do reject, what exact limit would you enforce? For example, max tokens or max bytes per message? And where would you enforce it in your flow?
Yeah, I would enforce max tokens because that's where our primary cost comes in, the number of tokens that we send to our AI models.
Max tokens is the right unit, since it maps directly to model cost and latency. Where would you enforce it first? In the client, at the API layer, or inside the chat service right before calling the model?
Well, if we do it at the client level, that could be hacked at the API layer. Could make sense. And at the chat service right before calling the model could increase latency and complexity. So let's do it at the API layer so that it's a little bit easier for us to keep track of things.
API layer enforcement is a good call, since it protects the expensive model tier and keeps behavior consistent across clients. Now, let's shift to the model service. With 1 million concurrent users and an under 1 second target, how would you keep inference latency low under load, especially during traffic spikes?
So we have our state store. Is that sufficient? Like, what should we do, and what kind of databases are we working with?
The state store helps with context, but it does not solve inference capacity. For the model service, you typically need a dedicated serving tier that can batch requests, autoscale, and shed load gracefully so P99 stays under a second. Let me extend your diagram to show the key inference pieces. Here, the chat service calls the model service, which can enqueue work for batching and smoothing spikes, and workers can use a cache for repeated prompts. What kind of model are you assuming for V1, like a small fast model or a large one? And what P95 latency budget do you want to allocate just to inference?
Yeah. What does it mean to allocate a latency budget to just inference? So you're saying, hey, our program end to end has multiple components to it, including inference. And the P95 latency budget means how long, what the latency is for inference. Is that correct?
Yes, that's exactly it. A latency budget just means you take your end-to-end target, like under 1 second at P95, and you spend parts of it on each step, like API overhead, state fetch, inference, and persistence, so you can reason about where you need to optimize. Given a 1 second P95 end-to-end target, how much would you allocate to inference versus everything else?
Well, inference definitely takes up the most time. So let's say 800 milliseconds.
800 milliseconds for inference is a reasonable starting budget, but it is tight at P95 if you also need queuing and any retries, so you will want to keep the queue mostly empty under normal load. Given that budget, what is your plan when load spikes and the inference queue starts growing, so P95 would blow past 1 second?
Well, we could reject some of the requests and say the model is busy right now.
Rejecting some requests is one valid form of load shedding, especially to protect P95, but you usually want a graceful ladder. First autoscale capacity, then degrade quality, then rate limit, then hard reject. If you had to pick one degrade quality option before rejecting, what would it be, for example, switching to a smaller model, reducing context, or disabling personalization?
Let's switch to a smaller model.
Switching to a smaller model is a solid first degradation step because it preserves the user experience while cutting compute and queue time. How would you decide when to switch, for example, based on inference queue depth or observed P95 latency?
Yeah, so we could do it so that, well, let's go with our queue, right? Because for latency, if latency increases, that could be some other underlying issue, and we should go ahead and fix that. For inference queue, that means that if our inference queue is growing, that's a more direct way to see that we are having an increase in latency. So how about if we see if the queue extends past a certain amount, where that the queue is growing rather than shrinking, then we should definitely send and switch to a smaller model for all new queries. And actually, maybe we should do those for like the tail end of our current queue too. We should move some of them over to the small one. We should take off of the queue with an instance of the small model and an instance of the big model.
I like the queue depth trigger, and splitting traffic across a big and small model tier is a common pattern. One caution, moving already queued requests can get tricky, so I would usually route at in-queue time and only reroute if you can cancel safely. What would you use as your switching signal and threshold, like queue wait time estimate versus raw depth?
Yeah, can you give me a minute? Okay, so thanks so much for checking out this systems design interview. I'm gonna go ahead and cut it here so that we have some time to look through your feedback. But this is a demo of how we can together learn about how to design an AI chatbot system. So let's see what kind of feedback we get from this. Awesome. Let's look over our feedback. Okay, so go 3.4 for requirements gathering. Seems like we could be a little bit more specific about the things we say. Daily active users instead of number of users. System architecture. Yes, we can propose more things ourselves. Technical depth, we can practice decomposing latency. And okay, great. What to practice next? Awesome, we can practice capacity, estimation, trade-offs, and so on. Okay, let's look at our replay. So I just want to show you this. You can actually see our edits over time, like updates to the whiteboard and our chat history and things like that. I'm going to go ahead and enter coach mode so we can see what
Let's
we can
walk through
improve
your
on.
system design interview for the AI chatbot. You scored a 3.4, which puts you at the competent level. I'll show you where you demonstrated a great grasp of AI constraints and where we can sharpen your architectural independence. Feel free to ask me questions at any point. Great job dreaming big here. This was a bit broad to start, but it set the stage for the deeper dive into scale that followed.
Okay, so what should we say instead of this? Let's see what it says.
Instead of the broad number of users statement at 20s, you should have immediately quantified the scale with specific targets like 1M daily active users DAU or 50K peak concurrent users. Pair this with a concrete performance goal, such as a sub 2-second P99 latency for the first token, to turn a vague objective into a measurable engineering constraint.
Okay,
Nice
that makes
choice.
sense.
Placing the token enforcement at the API layer is a solid architectural decision that protects your downstream services.
So we just did this randomly, so let's see what the alternatives are.
One alternative is moving enforcement to the model service layer, which ensures the logic is closest to the LLM, but may lead to wasted resources if over.
Okay.
At this point, you relied on the interviewer to introduce the state store concept. Next time, try to anticipate the need for a hot data. It's okay to ask for clarification, but try to practice decomposing end-to-end latency into specific.
Okay, how do we practice this? Let's see.
To practice latency budgeting, pick a target P99 latency, for example, 2 seconds, and assign specific millisecond costs to every hop in your architecture, such as network transit, state store retrieval, and LLM inference.
Great.
While
Okay.
rejecting overall,
Awesome.
you showed
Okay,
a
overall,
solid
seems
understanding
like
of
we had
modern
good
AI
feedback.
patterns.
Well, thanks for checking this out and reviewing the feedback with us. I'm going to go ahead and actually share a replay so you can check this out yourself. Let me know if you think you can beat this and take on this challenge. But yeah, the link below will show you the feedback, the replay, and the challenge. So comment in below. I want to know what you got as your score, and feel free to share your replay as well. Thanks again.